So today I'm excited to have a great conversation with Ian Cutress. He is the host of the TechTechPotato YouTube channel, and he has spent much of the last decade closely monitoring developments in AI hardware and software acceleration. In addition to covering all of the major players that you've come to know and love, including AMD, Intel, Tesla, and of course, NVIDIA, he's also tracking the progress of nearly 100 AI-related startups. And so today we wanted to have kind of a wide ranging conversation. And we're going to start with some Tesla related things and then branch out from there. And so let's get into the first question, Ian. Dojo. Is it a success? Is it a failure? Is that to be determined? What is your take on Dojo? And can you give the audience a little bit of background on how it is that you came to have a well formed opinion on this subject?
So to answer your question in an immediate context, Dojo is more of a failure than a success at this point. And I come to that conclusion after spending time going through the architecture, the way it's constructed, the fact that it's not just one piece of silicon, one chip, it's actually an array of wafers with support silicon attached. And the fact that what the Tesla team did here is build raw infrastructure for AI. It was a big undertaking project. You can't remove one piece without it not working. You have to have everything working together. That's a very big project. I spent time poring over those details when it was announced back in 21, and then the update again in 22, Tesla AI Day. I got time to spend. I've spent time with the architects on that project, understanding why it was built, what the workload it was aiming for, who the target was for that, and ultimately the answers are the target is themselves. Despite what Elon said, I'm pretty certain they had no real expectation of offering it externally. And the workload it was used for is essentially labeling their video training data. We can go into that in a little bit if you like. Um, what makes me more pessimistic is that it has been almost 2 years since we heard anything serious about the Dojo project. Elon was saying at one point, I think by the end of 2022, there'll be, I think he said either one system is being brought up right now and then 7 in the Bay Area by the end of the year, or 7 by the end of 2023. We've heard nothing. We've also seen reports that Tesla's buying more GPUs. If you remember, Dojo was said to, if we have to keep buying GPUs, then we can't get this to work. We have to build something that's more efficient. And we haven't heard anything on that. And on top of that, I think perhaps more importantly, is that a number of the key team members of the Dojo development have left. The head of the project has left. A number of the senior designers have left. A number of the physical design and test and validation. I'm not sure to extent how much of the team is left or how many of them have been replaced. So in an industry that talks about chip and chip design and chip development and chip deployment, one of the things we look for is who are the key individuals in that team? Where do they go? What companies do they turn to? How successful have they been? And how successful have the projects been? Usually in those circumstances, we're looking at silicon, we're looking at products that eventually make their way to market at retail or in servers that go into data centers. And we can look at the revenue gain and the customer distribution, see how successful a project is, or whether a project gets mothballed and that person gets funneled off to a different division. Tesla's different, right? They're building a chip just for themselves. They have to get it to work, and it's this massive undertaking. It does epitomize, Elon's nature of let's go for the moonshot and make sure it works. This is a lot more intricate than that. So when I look at the Dojo project as a whole, I'm worried that there hasn't been much news in the last 18 months, 24 months. I'm worried that a majority of, or a good number of the key personnel in that team, a team, by the way, that has had success in the past at other companies, have now left, and this continued reliance on NVIDIA GPU purchasing. we're at a stage right now where machine learning is can be difficult if you're not using the latest models, the latest software packages, the latest production environments in order to get high accuracy, high performance, low power, and a lot of that today is being done on NVIDIA. You go build a brand new system from the ground up with a custom architecture. Okay, it's more power efficient and more performant, but you still got to put the software work in. And we're seeing AI startups fail very much on the software side, even if the hardware is great. So ultimately, too many question marks, and some of the answers we have had are not positive, to be blunt.
Just a brief aside right here. A little bit later in the conversation, Ian and I do discuss the news that was released in January that Tesla is now building a $500 million Dojo based cluster there in Buffalo, New York. And this was a piece of news that had actually escaped Ian's notice. He wasn't aware of it when he made these specific comments. And in talking to him briefly about it off camera, he did say that that was an encouraging piece of news, which kind of brings us a little bit back closer to the TBD thing. But with that said, a lot of the comments that he's made here do stand. There's a lot of question marks, and we haven't seen the full potential of Dojo being reached. And of course, Tesla does seem to be aggressively moving forward with H100 purchases from a variety of vendors. Now, we've not only seen Elon purchase them directly from NVIDIA, but now also for Tesla getting those from Dell, and then potentially even leveraging H100s from Oracle for XAI. All of which kind of lend a little bit of credence to the fact that Dojo, at least at this point in time, isn't as far along as Elon had hoped. That said, I do want to point people to the Tom's Hardware article that referenced TSMC's latest announcement that Dojo is being and has been developed on their new system on wafer process, and that the next generation of that, which will be coming out in 2027, it should allow this Dojo chip to be 40 times more powerful than it is today. Whether or not that will allow them to catch up and potentially displace more NVIDIA hardware at that point in time remains to be seen, but I did want to just leave that note in here for viewers. So, yeah, it sounds like we can't say definitively that it's a complete failure, but it, like you said, question marks, and it doesn't sound good at this point. How much of that do you think um, tracks to, I think there's a couple of possibilities here. When they initially were architecting, the version 1 of the Dojo chips, it was before AI started to make this pivot into the transformers. And especially since then, the version 12 of full self-driving, it seems like they are really relying on a lot of the more recent innovations in the way that AI models are developed. And so they've kind of pivoted on how they're building FSD, and the Dojo chip seemed like it was probably architected in an era of AI that didn't have that on the roadmap, and so the hardware wasn't maybe designed in a flexible enough way to handle these new types of training loads. Is that part of it, or do you think they're struggling because we know that CUDA is a very difficult moat to overcome. One of the things that Jonathan Ross has said is they probably have, a team of over 5,000 software engineers internal to NVIDIA, and then there are many more external to NVIDIA that all work on, trying to do the very difficult work of getting from this interface that is, PyTorch into CUDA all the way down to the actual silicon of NVIDIA GPUs. So is that the bottleneck that you think is more likely? If you had to handicap it, which of those two problems do you think is more of a challenge for Tesla to solve?
On the face of it, probably the latter. Though again, NVIDIA's trying to cater to millions of developers worldwide. Tesla only has to cater to themselves to a certain extent, so it can afford to be rough and ready. To your first point about the way that AI has changed transformers, it's ultimately two eras of AI. You have what's called the convolutional neural networks, and then the transformers, CNNs and transformers. Convolutional neural networks were and have been and are still applied today for video work. So this is identifying people on video, facial recognition. It's what your smartphone uses to determine whether you're looking at a cat or a dog or a tree or snow when it does that image identification. And transformers, on the other hand, are mostly used in decision-making and generative AI use cases. This is the more sort of chat GPTs and stable diffusion, image generation, audio generation, that sort of thing. So if we were to break down what a full self-driving workload is, it's identify what's in the image and make a decision. One part of that is standard CNNs, and the other part could be accelerated by transformers. When it came to Dojo, the key part of the two Tesla AI days that I think kind of went under the rug for most people is what actually Dojo would be used for. And it was clear from speaking to the people there that the first workload for Dojo was just going to be this sort of video image labeling, this identification of the data that they had coming in from they're introducing more video to the training data set, and you have to label it. So doing things like image segmentation, finding out what in the image is a person, is a road, is a tree, is a sign, and then being able to put a label to that. Historically, that always used to be done by a person, right? The person would say that, this is a dog running across the road, or this is a bike. If you can get a machine learning workload to label video for you, it speeds it up. And they had an argument of saying, it would take weeks to label a data on a standard video data on GPUs using 720p cameras or whatever, and they wanted to reduce it down to seconds with Dojo. So ultimately, that was going to be the first workload for Dojo, and that's what they were profiling it against initially. The fact that they were going to have 1 to 7 of these systems, in Palo Alto, that's what it was going to be doing first. And that was a workload I'm pretty sure the architecture was designed for. Only then was it going to, once it established that, was it going to work on, well, how do we improve the algorithm that makes the decisions on what to do given the environment? And of course, that is very multifaceted, and the way that transformers have evolved in the last 2 years means that people are doing multiple things on how to adapt the transformer. You're doing graph compilation, so it's how do you solve that problem with the data you have, and transformers are being good at doing that sort of the generative decision making on that side. I will say that with the labeling of the video, one of the things that people are doing now is how do we create artificial data to help train these algorithms as well. So this is if you're driving down a road, how do we make it look like it's snowing? How do we make it look like it's raining? Can we do that with the data we have? And Dojo was meant to do some of that as well. And NVIDIA does this a lot in their robotics training environments. Can they put a theoretical robot in a theoretical environment and see how it reacts, rather than actually doing it physically in the lab or in the real world? If you can do it computationally, then you arguably save money, time, personnel. So even with all that workload, even with all that planning, you still obviously have to do the software. And as I say, people got hung up on the fact that Tesla or Elon had said, due to a question at one of their AI days, will this be available to other people? And he said, that's the eventual goal. I think people streamlined that comment into almost saying it would be immediate. Dojo had some pretty significant architecture decisions made that meant it couldn't be used by multiple people at the same time. So in the cloud, we talk about having a server that can be eight people can run on it at once, all isolated, um, and so you're sharing resources. And I think a holistic view of what a dojo could be like would be as if you had these 120 wafers, and everybody could get one or two for running their workloads, whatever decided to fit on the system. But the system couldn't handle that. You had to run one workload at a time through it, and that was one of the fundamental architecture decisions the team made. Um, as I found out going through the details when they announced them, maybe a generation 2 or a generation 3 would have fixed that. But no, the fact that it was going to be all internal means that everybody's using internal tools. They may be derived from PyTorch, from TensorFlow, from Cafe. Um, but if you wanted to write software for a dojo, you would have had to work for Tesla. And it would have to obviously go into Tesla's goals of what they were trying to achieve. And ultimately, at the end of the day, something shareholders. So um, it's from the outside, it's from my perspective, from where I stand, it's almost straightforward to pinpoint where the hardware was trying to go, but the software would be the big question mark on that front. I wouldn't say it's a limiting factor in the same way that AI hardware vendors that aren't NVIDIA today are trying to get into the market, are trying to build a developer base. Tesla arguably would never have to do that. So
coming back to the success or failure question, I can't help but notice that they have laid off their entire auto labeling team. And Elon has talked about putting a $500 million Dojo installation there in Buffalo, which happened to be where they were doing the auto labeling. And if he's saying that we are no longer compute constrained, that should mean that the entire pipeline of getting data from cars into the training cluster is pretty much completely automated. And so there has to be, a pretty significant portion of auto labeling that's going on. Do you think that that entire auto labeling workload is probably operating on Dojo today, and they're looking to just scale that up as their training cluster scales? Or how are you thinking about that?
unless you know how much new data they're ingesting at any given time, it's a hard thing to understand. We haven't seen any information about how much data a dojo can process, whether it's several seconds per real world second, or whether it's several real world seconds per second of video. It's um, and I think a portion of that is also if they run it on Dojo, they're probably also running a similar workload on GPUs. At least they would have done initially to make sure that it produced the same result. Making sure that there was software verification of what was being going on. But if he has announced a new system in Buffalo, the whole point of building the system is let's automate these workloads, let's get it in. Hopefully there's enough levers and switches that the security guard on duty can go and pull one if something goes wrong. If he's the only person left in the building. So
Cool. Um, so I think maybe this is a good time for us to then pivot out to just if Dojo doesn't seem like it is doing a good job at replacing Nvidia hardware to do the training, and we know that Elon has purchased, a very large number of H100s, um, and rumors are that there are many more that are inbound. What is it that makes this training job such a difficult job to do, especially with the, constantly evolving nature of the way that the different like the AI models, whether it was CNNs or are CNNs for certain workloads, are transformers for other workloads, and then potentially, a year or two from now, we could be on a whole nother generation of types of architectures. Like, why is that such a difficult problem, and why is NVIDIA basically in a temporary monopoly position in relationship to that challenge today?
well, ever since the first kind of CNNs ramped up in performance, so somebody said, "Hey, we can do this in a GPU." Um, NVIDIA is a company that rapidly iterates its silicon. Once every 12 to 18 months, we get a new architecture. And it also just happened to come out at the same time as ray tracing. Who knew? For games. So this ability to do these large matrix operations became, let's accelerate that. Then obviously the theory of the research catches up, and this is where we move from CNNs to transformers. And with a transformer, you have a lot more of serial operations, things that aren't just matrix multiplications in that workload. So you need ultimately hardware that can deal with both the matrix multiplications and what they call the special function workloads. So anybody that was building the CNN stuff before just went all in on matrix multiplication. And that's why that hardware isn't necessarily good at transformers today. But even if that was a limitation of Dojo, you could still put out systems to run CNN workloads and then still use NVIDIA's H100s for transformer workloads, because it turns out they're actually really good at that. And it does have the biggest software base and the biggest adaptation. It's it's the fact that NVIDIA went into universities 15 years ago and said, we're going to teach you how to program GPUs for compute. Now, in their minds, they were thinking high-performance computing, massive supercomputers, nuclear simulation, oil and gas, that sort of thing. My claim to fame is I took the first ever CUDA course outside the US. A finance professor at my university was given a bunch of money by NVIDIA and say, run a course. And so he did a trial, a beta version, and I went to that. And that set my course for my schooling at any rate. But they've had the ability to put engineers, software engineers, through 15 years of people coming up through university, learning CUDA as a first language, essentially, in their programming skill set. So people are thinking very much in how do we compute in a parallel SIMD way that the hardware goes through. And now they're applying that to the theory. Because don't forget, AI isn't new. AI was thought about 30, 40 years ago. It's only now that we're taking these new computing paradigms with the theory and saying, how can we bring these together? And that's kind of what transformers has become. And there's layers upon layers within transformers as well, don't get me wrong. And we do see different hardware in the market coming up through that. When it comes to training, I actually was given a great slide that showcased the nature of a training workload. Training is a very thick, cubic, defined workload. You know how much data is going in, and you kind of already know what's coming out in terms of the size, and you know what your workload is going to be over time. You know how long you're going to have to run your GPUs for, or your Dojo system for. When it comes to actually using the results of the models that come out, the inference side, that's lumpy. You could be doing 3 inferences per second. You could be doing 30. If you're in the cloud, say, for example, full self-driving, that may be doing 300 inferences per second at some points. But if it's a really messy environment, it might be doing 600. So how do you build hardware to deal with that in a very power efficient way? And that's arguably the next generation of how we look at AI hardware and AI data. Everybody's kind of building for the generic right now, whether that's CNNs or transformers, and then making a small version for inference. We're moving into a future where training is guided by the end hardware. If you know your model is going to run on a FSD chip, perhaps we can build the model to be optimized for the FSD chip and not just a generalized math model that comes out of these things. People are trying things like retrieval augmented generation, RAG. How do we feed the model with data we already have, such that we don't need to do extra training and essentially cut some time off the training side? And then how do we distribute it? Maybe you need this model works in this region, but this model works in that region, and this model works in that region because that region has more sandy roads or has a different traffic light system, or has different road signs, that sort of thing. So you end up we're moving into an era where a lot of this stuff is becoming highly optimized for specific in for NVIDIA. It's like specific customers, specific verticals, and you can bet your bottom dollar with things like Tesla. It will be specific vehicles in specific regions conforming to specific standards. And then as we move on to the ultimate goal, level 5, autonomous driving, you can bet your bottom dollar what you need for level 5 in one region is going to be different to what you need in another. And how do you keep that data set active and updated? And how do you make sure you don't overfit your data? One of the things in AI right now is if you feed your model too much data, it starts going, it gets better, better, better. Oh, and now we're starting to get worse with the accuracy of these things. So it's also a case of finding out, well, where exactly is the sweet spot
That
for all
point.
of that. Yeah.
So when you say that, it will need to be different, if we were to look at level 5 in one geography versus another, different from a
Yeah.
hardware perspective, or just different from a data curation and a model perspective? Where would it need to be different?
So the latter first, as in the models will have to be different. If there is a business reason where they could make hardware that was more optimized for a given region, given the fact that they already have the models for that region, the bar to do that would be really high, by the way. Then you could see customized silicon, customized hardware per region. But that's taking like the nth of the nth of the nth of optimization there. It's
So
or
basically, after we have a good, general solution that works pretty well in most places, then if you want to keep making it better, you could potentially envision a Western world version of hardware and then an
mhm.
Eastern world version of hardware that were
But
specifically.
I mean that's a good point. An Asian FSD L5 would have to be able to recognize all the different character sets in Asia, whereas there's only a few in the Western world. So that would be a different algorithm for image identification, for sign identification. Once you've already done the segmentation on the image on the inference side in the vehicle, it then has to work out, does this sign mean stop? Does this sign mean go? So not everyone in the world uses symbols. A lot of people still use words, and then the symbols are different in each country anyway. So um, a holistic person may say, let's get one big model that does everything. But as even Tesla have said this, one of the new features we're moving into now is this world of mixture of experts. So it's not just one model that does everything. It's one model that then decides what other model to then run. Um, and then that may be a cascading decision tree of optimized models going down. And that cascading tree could be different for different regions based on language, context, weather. There's going to be one model for snow versus one model for rain versus one model for tornado. You have to identify the cow flying across your viewpoint.
Going back to Twister. Um,
Yeah, or
since
Sharknado.
we're yes, since we're talking about FSD a little bit here, it does beg the question: how impressive is the hardware 3 computer? Given we've got millions of these things on the road,
Mhm.
is there a more impressive piece of inference hardware that, especially given the power envelope that it operates inside of
Yeah.
and the sensor suite that it's attached to, that is actually in the hands of customers at scale today?
Some people may point to Mobileye solutions. I know there's a few vehicles in China that are running those. I've actually had a chance to go into a level 2 plus and a level 4 Mobileye solution, but the level 4 one was they had a server in the back of the vehicle. It's I think everybody's getting to a point now where they understand just how much compute is needed. to get to a fully self-driving environment, and then it's just the power and the size constraints. This is why people will always point to, well, long haul trucking is perhaps the first point of call for self-driving, because they have the space, they can arguably consume the power, whether that's electric or gasoline or diesel. Um, that's where it's going to be in. And I think one of the major issues for actually deploying in devices today, and we're not only seeing this in cars, we're also seeing this in smartphones and laptops. This year's a big year for the AI PC. Um, Being able to provide the needed compute at a small size, at a small power envelope, and have the response needed is vital. With PCs and smartphones, you're just asking Copilot or doing search. That's not life threatening. It's not regulated in the same way that self driving is. So that has to be, accurate to, again, to an nth degree. And at least with FSD3, they built in a good buffer. That's why it's been deployed for so long. You can question whether it's enough long term to go up that chain to level 5, or whether it'll just simply be a level 4. Or it one of the techniques right now in machine learning is, how do we use fewer calculations? How do we need less memory accesses? How can we compute in fewer bits? This thing called quantization, if you've heard of Int8 or BrainFlow 16 or FP4 is the new one that's going around, and there's new variations of that called block float, and that's definitely a rabbit hole you can spend a degree going down. People are trying to find quicker, low energy ways to do these operations, and that's still arguably, when it comes to machine learning, in its infancy, which makes anybody who has hardware today think about, well, what do I need to build for the hardware in 3 years? Can I get by on what I have, or do I need to build something new? And what does that need to do? And can I predict what happens in the future? Because design cycles for hardware are so long. In the automotive world, it's, historically, a new car platform takes 7 to 10 years if you go to the standard car manufacturers. At least with EVs, that is kind of, that time cycle is decreasing. But machine learning is moving fast, and a lot of these techniques have to be validated and pass, the regulation in different areas if they want to go fully up that way to level 5.
I don't want you to speak out of turn on this if you can't, but if you can, I would love to know, a lot of the EV players in Asia and China specifically seem like they are on the fastest development timelines in comparison to Tesla of any of the other automakers. What are you seeing as far as how long it takes the fastest next player, and if you can, who would that player be as far as the shortest development cycles?
Yeah, I don't think I have enough knowledge of that market to explicitly say who or what. Um, I keep bringing up the term regulation because the technology is moving faster than the regulation. There's this famous graph of, if you look at what areas of the world are best at certain things, you've got Asia's good at silicon manufacturing, America's good at 5G and wireless and things like that. Europe's good for regulation. That's the one thing we have the crown on. And if you would say, well, what's the worst, what's the lowest in regulation, you would point to perhaps some of the Asian territories, where almost anything goes. So you could see some, unofficial, fast deployments of perhaps what could be considered a level 4 or beyond, even though it's technically not a regulated. But then we get into the fact that if you're running in a mode that isn't regulated and you're in a crash, and legal implications therein, it's how risky do you want to be, and how well can you pay off your fellow government relations.
Yeah. Which, is an interesting data point when you think about the fact that it looks like China will be one of the first markets to get robotaxi I'm sure that it will probably, or from Tesla specifically, or at least that's what they're kind of aiming at. I think that it's likely that we could see some individual states where Tesla's doing some kind of, geographically isolated projects as well. But I do think that that is an interesting go-to-market strategy that it seems like probably is influenced by the regulatory environment as well.
It also the business use case. The business argument for robo taxis is pretty forward. You lose the driver, so you save a bunch of money, and you just need one person in a call center somewhere that has access to 50 vehicles. So you'd be willing to pay what, another 50% on top of the car price to be able to enable that, because your return on investment comes by through pretty quickly. Um, I did a poll on my Twitter, um, probably a couple of years ago now, just asking how much would people pay for fully self-driving on a personal vehicle, and most people say, above the list price, above the retail price for a brand new car, and over half the respondents said 10 to 20%. So, I mean, personally, I'm more like of the 40 to 50%. You know, my time is, I can't regain my time. If I can pay to get extra time, then so the business model is well suited to paying premiums on that sort of stuff.
I've run a similar poll, and it seems like for personal use, a lot of people, they don't value it that high, which leads me to believe, because I think intrinsically the value is much higher than probably double the price of the vehicle, that this will end up being, fleet operators, because they're the ones that recognize and are willing to, invest the capital necessary to provide that service. Um, so it'll probably be a lot fewer over time personally owned vehicles that are, being provided as robo taxis.
Or they could be given to consumers as leased vehicles. So it's almost a robo taxi kind of. But then you only need one person in a call center for every 5,000 vehicles, maybe. So there's going to be many ways in which this is sliced.
Exactly. Yeah, there are so many different go-to-market strategies that could exist, and I'm sure that, once the technology has been proven out, that we'll see a lot of, attention and VC funding and startups, trying lots of different models.
Yeah, for sure.
So, coming back to AI hardware, we kind of have training, and that's one challenge, and we've talked about that with NVIDIA. And then there's inference, and, one of the things that you said actually was a little bit counterintuitive for me. I've always thought about training being the harder problem, because, the process for training, so for the listeners, when you're doing training, you have a very large set of examples, and you push those examples into a supercomputer, and it has to push it forward through a predefined black box system, and then say, okay, did we get close to the result that we wanted for an example? And then if yes, you know give it lots of gold stars. If no, then you spank it, and then it goes backwards through that. And so the way that you flow those examples through forward and backwards creates a lot more of a complex, information. Like, you're moving information around in a much less predictable fashion, or at least it felt like it was much less predictable to me than in inference, where you've got the model already done, and now you're just saying, okay, here's the examples that I'm seeing in front of me right now. Now transform those into the actions that I want afterwards, and it's just one single pass. You put in, if it's pixels, if it's, ChatGPT, then it's a prompt, and it just spits it through, it pushes it through that black box, and then out comes your result on the other side. Um, but from what you've said, that the is the difficulty in doing that a function of, say, some prompts are more difficult to process, whether those are pixels or words, or is it just the variation in, the number of users who might be on a system at a given time? What are the challenges that make those inference workloads hard?
Well, so Well, one way to vision training versus inference is imagine training like a university degree, but somebody gives you all the books for those 3 4 years on day one, and you just have to chug through it. So at the end, you have the information, but you've just spent 3 to 4 years to get there. You spend the next 40 to 50 to 60 to 70 years of your life recalling that information. Right, so you're using that model, that understanding you've built up over those short amount of time. Yes, it was heavy, it was dedicated, you were focused. But anytime you recall the information over the next few years, sometimes maybe focused, sometimes maybe tangential. Some days you may realize, oh, there's a relation between these different things that I hadn't realized before. Training versus inference is the same, on a larger scale. You have this dedicated, as you say, pushing forward and back, this sort of back propagation technique. But you have a rigid block of information that you just have to process, and you have a time to process that. When you have the inference workload, say like ChatGPT or whatever, you now need to use that in lots of different circumstances. Maybe you're distilling it to be a help bot on a website. Maybe you're now making it so it responds to voice commands. You're taking small bits of that information, distilling it. But take the prompt example. Certain time of the day you may have 10,000 users. Another time of the day you'll have 100,000 users. Some users will want responses that are 2,000 tokens long. Others only need 50 tokens long. The amount of workload in each of those inferences is different. So it's lumpy. So it's not as dedicated. It's not as focused. But ultimately, if we look at where machine learning is, go up to the 30,000 view, everybody right now is focusing on training because that's the thick workload that we know takes time and takes effort, and you need all of these resources to do. People used to, I'm not sure they do much these days, they build a fund for their kids to go to college, right? So it's you dedicate time, money, effort, and resources to doing that workload. And then, but ultimately, where you make your money, the revenue in the AI business, it's all about how do we make money out of this thing? Where do we see the value in it? We have to run inferences. Do we know when the inferences are going to come? Do we know how big they're going to be? Do we know how detailed they have to be? Perhaps not on day one, like we do with training. We know how big the training workload is on day one. But that's ultimately where the revenue is in this industry. How do we apply these models to hundreds, thousands, millions of people, and however they use it? So ultimately, people are under the impression that, if we look at the lifetime revenue of machine learning, it's going to be very much skewed towards the inference because people are going to pay for the inferences. Again, it's like ChatGPT. How many words do you pay for when you put in, like somebody paying for your expertise? You're a plumber. You've done your years of experience training. Now you have to go do your workload. Computer scientists or financial people pay you for your time. People pay you for your expertise. That is essentially the inference here. There is, to your point about, are there some workloads that are heavier than others? The most ways in which generative AI is distilled is this thing, what we call a token. Token is a bit, I argue with people whether we should be using the word token or whether we should use, we should just say words per second. On average, a word is about 1.2 tokens. It's annoying like that. So in the context of ChatGPT, where we're dealing with text, people talk about how many millions of, what is the price per million tokens? So ChatGPT 4 costs about $75 per million tokens, so about every 800,000 words. So it costs $75 for a Bible, for example. That's how much that inference costs. If we were to say to ChatGPT 4, go write this out and we need a response this long, you could argue whether it's accurate or not. When it comes to video, I actually got some numbers from Google about this. You've heard of the phrase, a picture is 1,000 words. Well, according to AI, a picture is 216 tokens. So that's roughly the conversion factor of what I've seen on some of Google's stuff. So generating video, we've seen some things recently with Stable Diffusion and Sora. That's expensive to do. Um, Most of the generative AI workloads are really expensive computationally, and therefore going to be expensive, to the individual, to the business. These more CNN type workloads, the let's just analyze stuff rather than make generative decisions, they're pretty cheap by comparison. That's why it's pretty cheap for a security system in a store to do image recognition of everybody that comes in. It's actually fairly cheap computationally. You don't need the latest and greatest RTX 4090 or H100, A100, or B100 now to go run that. You can run something. You can run 100 cameras in a store on less than 100 watts of GPU compute power, and that's all it's doing is tracking people going around the store, or if it sees an incident happen or things fall off the shelves, because it's not generating significant action. The only thing it's generating is clean up on aisle 3, or this person has been in the store 18 times in the past 2 weeks, that sort of thing. It's the generative stuff that's the market is going to rally around. That's why you hear every company saying generative AI, generative AI, generative AI. I actually do this thing on my YouTube channel where I take a keynote from like an Intel and AMD and NVIDIA and cut out every time they say AI or generative AI or artificial intelligence, and you end up with 200. I think the leader on this leaderboard is Intel. They said it almost 200 times in less than an hour, because the more times you say it, the higher your stock price, I think. That being said, Apple just announced new iPads, and they only said it 7 times in 40 minutes. So it's there's very much hype.
And it does seem like the people that are trying to, run those inference workloads on NVIDIA hardware, that seems to be, a very, very expensive workload, almost to the point of being cost prohibitive, that people, most people don't want to pay what it costs in order to run those workloads. And so this seems like an area where we've seen a lot of focus from basically every, hyperscalers are kind of doing roll your own solutions to bring down the cost of inference, whether that's Azure, whether that's AWS, name your hyperscaler cloud provider, and they're probably trying to do their own chips for inference. But then you also have players like Grok that are really, kind of going to a whole different level of simplification and abstraction to try and speed up inference. And it seems like it's actually working very well for transformer models. Um, what do you see, I guess, in that realm as far as, can we bring the cost down, and who are probably the most significant players doing the most exciting work to accelerate those cost declines in your work, or in your estimation?
Yeah. So I mean, NVIDIA is trying to be the everything to everyone, so they have to be able to support everything. The reason why the hyperscalers are running their own is because they have internal workloads that are absolutely massive. We're talking, petaflops, exaflops, massive internal workloads. Think about what Amazon has to do to build a very accurate recommendation engine. Or if they're doing work for, say, a defense provider, maybe there's a bunch of data they need to go work on. They have a very specific workload in mind, so they can go build their own chip. They can entice people with money. There's always a good lubricant for these sorts of things. Get good chip designers, either take off the shelf designs from ARM, or go roll their own and basically over optimize for their given workloads. And it's this differentiation. We talk about GPUs. Don't forget CPUs exist, and now we've got these dedicated chips called ASICs. As you scale from CPU to ASIC, your configurability, your programmability goes down, but what the workload you run speeds up. it's faster, it's more power efficient, and it's cheaper to run. If you are an Amazon or an Azure or a Google with these massive internal workloads, you can either go and spend billions of dollars on GPUs to run your workload, and then your cost due to the power consumption, your daily cost is very high. Or you think, if I spend 200 million designing my own chip, put that in my data center, run it at a tenth of the power and get the same performance, or even it does stuff that NVIDIA can't do because I know my workload, then you're going to take a punt and see if you can do that. Ultimately, this is what Tesla did with the Dojo. They said, we have this dedicated workload, let's go build our own chip because we can try and get it cheaper and faster. There is a slight difference between chips that hyperscalers build for data center inference for their own workloads versus customer workloads. So this is hardware you can access on the cloud. So this is kind of what Grok is trying to do, and a few others. Let's build chips that would arguably replace NVIDIA in a data center that can be used for cheaper inference. The problem you have there is NVIDIA's hardware does both training and inference. Usually people, if they train on NVIDIA, they prefer to do inference on NVIDIA, unless they've got a highly technical team that can do that conversion. If you keep it at a high enough level, this sort of TensorFlow PyTorch, then switching between architectures can be a lot easier. And this is what Grok's trying to rely on. The fact that we support these high level semantics such that it is a very easy, case to flip. And then their argument is, okay, we can beat everybody else's performance at a better power. Come buy our stuff. But that being said, it kind of sounds like Grok's turning into a cloud provider at some level. They don't want to sell hardware. They want to rent it to you by the second or by the minute in the cloud. But other companies are going down this route. It's if we design a chip specifically for the financial markets to do inference, can we get them to go invest in this? But then they have the problem of, well, all the machine learning models for the financial market were probably built on NVIDIA. The training was done on NVIDIA. What I'm finding is that the bigger the customer, the more willing they are to go down into the low level, down to the metal, they call it, and optimize it at an instruction level. They don't care about this high level support and the high level semantics. They will take the hardware that fits best for them and just dive deep and go straight into it. Which takes time, that takes expertise. There's only so many experts to go around. The US right now is having a shortage of optimization experts in high performance computing, and AI is so new that we're only now getting the first true graduates from the transformer era coming through. So there's going to be a decade of just engineer chasing. How can we optimize this? But then also, if we look at the business side, we've got a ton of companies that are trying to do AI as a service. This is like OpenAI with ChatGPT, right? What as a service people do is they have to look at how many customers do they think they're going to have, what are the capacity they need, and who can provide that. Do we go with this custom silicon from a startup that may not exist in 3 years? Or do we go with the tried and tested player in the market that everybody's optimized for, that we can just rent instances from the cloud already, from NVIDIA, NVIDIA through Amazon, from whoever. And we're seeing that while people would love to have low power, high efficiency, fast throughput, optimized hardware for their own workload, time to market is more of a driving factor. So while this current high demand for silicon is creating all these new silicon opportunities, if we're looking at a fundamental, middle management level of a lot of these operations, we just want what works and a price that we can get today, such that we can deploy it as soon as possible. We don't want to sit around for 8 months trying to optimize for this chip that some engineers out of the university of whatever have made. They may have $1 billion in venture capital funding, but I deal a lot with these AI hardware startups, and I track probably near 100 of them. This is between training, data center inference, edge inference, um, and there's about 30, 35 that have over $100 million in funding, and a few of these have even raised 100 million plus this year. So investment is still going high in it, but you'll find that it's this mix of the hardware has to find a niche, and it's the hardware companies that have the value add of something other than being not Nvidia. It's you're never going to compete with Nvidia with a slightly cheaper chip that does the same. You have to offer something new. You have to have this different angle. With Grok, because we keep bringing Grok up, their chip does this thing called batch one latency, and it's consistent. Usually, when you run a workload in the cloud, you have what's called a minimum service agreement. So you know that some inferences will take 10 milliseconds, but there might be 1 in 1,000 that takes 100 milliseconds. With Grok, they can clarify that every inference will take the same time, regardless of the size of the input. It's model dependent, so one model may be faster than another model, but they can guarantee that response every time is the same. That's why they can do demos of 300 tokens per second online, because they know every time somebody puts something into their system, it's 300 tokens per second. That's just the nature of the model. That being said, the way that they've scaled out their operations recently, they couldn't find a big enough market for that specific feature. So now they're talking about how scalable their architecture is. You can put multiple chips together in a very scalable way. In computing, this is like Amdahl's law. How much parallelism can you get out of a system? So they're going down that route. There is we've also spoken about Cerebrus. Not necessarily an inference play, more of a training play, but they're most aligned with Tesla Dojo in the fact that they're wafer scale. So their whole thing is let's put the equivalent of 80 GPUs on a single chip. And yeah, it costs 2 million, but they have high memory bandwidth, they have high power efficiency, they have good power efficiency. And they just sold $1 billion worth of systems to a strategic partner based in the Middle East. So they're working on language models in Arabic, and they're looking at modeling health data. So they're really active right now in terms of building that client base.
One of the things I've been curious about on that front, and I guess this would be applicable to both Cerebras and to Dojo, is that, obviously if you make a wafer and you've got a lot more chips that can talk together a lot more quickly, all in one place, well, that's great as long as whatever you're training fits on, the tile or that wafer. But does it really matter when you're going to these biggest, think like a chat GPT or a GPT-5 training run where you're going to have to coordinate racks and racks and racks and racks worth of compute, whether that's GPUs or, special ASICs or whatever it is. Where do you run into your bottlenecks there, when you're looking at those largest types of training runs, and do solutions like Cerebras or Dojo, do they even have a chance to scale up to those large workloads? Or will they have to, I guess, how much invention do they have to do to get from here to there if they're, not going to have access to NVIDIA's solution to this, which is these NVLink switches and all of those, their proprietary um, high high bandwidth networking for this exact type of training.
Yeah, so the phrase commonly used in computer hardware and software is feed the beast. How do we feed the beast? How do we keep the beast fed over time? And with a GPU, you're right, that's with HBM. The fact that the HBM can talk to the GPU in these sort of terabits per second time to keep all the compute units fed. Um, and you'll hear people talk about this, how how often are my GPUs idle? Are they active 80% of the time or 20% of the time? Is that an algorithm thing? Is that a data movement thing? And so we move into this realm of, what's memory bound, what's compute bound, and again, another rabbit hole. With wafer scale, the key point, whether it's Dojo or whether it's Cerebrus, is how do you get the data into the middle of the chip fast enough that when it runs out of data, you've got more ready to come in, and it's not bottlenecked by other data moving around the chip. So how it's called it's called streaming your data in, and as a result, if you look at the Dojo design and the Cerebrus design, they are actually pretty similar. It's a multi-core. It looks like a multi-core design, but half the chip is dedicated to holding weights and activations for machine learning models. Because if you're holding them on chip, it's obviously very fast. You're talking about petabits per second. But where you have to keep feeding the data in as it's doing it. Cerebrus say that their chip, for what they're doing, feeds data in fine and you stay compute bound. It's model dependent, depends what operations you're doing, how many special functions I mentioned that earlier that you're doing that perhaps reduces some of this activity. But they say they have no problem feeding data in from an outside network, and they've developed a system where you can chain multiple wafers together and stream that data in and broadcast it back out with no bottleneck in the memory movement. It's all compute limited. Dojo's a little different. The Dojo supercomputer was envisioned as 120 wafers. You might think 120 isn't a perfect square, and that's because they didn't run it as a square. They ran it as a rectangle. 3 wide by 40 long. And the reason why 3 wide is that their only connection points were the 2 wafers on the outside of the center one. That's the only way data can come in to each row of 3 wafers. And the point is, you have to get data to the center of the middle one in order to feed the beast. And they felt that that was the limit that they could ingest data in, to the point where they could keep it fed. That's why it's a 3 by 40 and not like a 10 by 10. That being said, if you look at how Dojo connects, the wafers connect to the outside world, you have connection networking chips that have a Tesla ASIC on board, one that they've custom designed with HBM on it. So even their own caching ASICs have to have HBM on it in order to feed the beast, to make sure that the data's coming in externally from their storage as well. It gets pretty complex, and the reason why NV Switch and NV Link and all these technologies are trying to exist. AMD is now opening up its Infinity Fabric to networking manufacturers as well, is when you go outside of one chip, you need a way to keep the data fed, or when the model doesn't fit on one chip. You have to wait to make sure that all the compute parts of the chip are fed in the right way. One of the startup companies that seems to have a good idea on doing this is actually TensTorrent. And TensTorrent is, the CEO is Jim Keller. He helped design FSD3, as you mentioned. And the way they're approaching it is all these chips, they have a computational unit that's repeated many times, almost equivalent to a core. So how many cores do you have? Cores between NVIDIA and cores between AMD are different and whatever. But normally they communicate to each other through high-speed interfaces built into the design. And it's how those interfaces interact with all the cores and outside the chip. That's where you get your bottlenecks in memory movement and data management. With TensTorrent, their philosophy is one core looks like one chip, looks like one system, looks like one data center. So the command to move data from core to core is the same to move data from one core to the chip on the other side of the data center. So they're using the same computational topology, the same computational semantics to do that data movement. Now, of course, it's going to be slower to go over there, to go over to the other side of the data center. But by keeping that consistent, it actually makes a lot of the software side of the management of the data very easy. People don't have to worry about, well, do I need to keep this data in this set of GPUs back until that one's done and make sure there's not, a blocking cascade or of data or what have you. People try and mitigate that through using PyTorch and TensorFlow, and that tries to manage it. But ultimately, it becomes a game of whack-a-mole of how do we get rid of some of these bottlenecks. And the way TensorTorrent is doing it is through essentially making everything look like an Ethernet connection. Ethernet is the most prominent networking standard in data centers today. And anybody who's ever written code for a data center to run on a server in the cloud has been involved with Ethernet in some way. NVIDIA uses something else called InfiniBand, which is optimized for latency, but has some scaling issues, which they're trying to mitigate through AI and machine learning. And the company that makes InfiniBand, Mellanox, is one that NVIDIA acquired a few years ago. So they're doing some deep integration between the GPUs and the networking, whereas everybody else in the industry has sort of decided that Ethernet's the way to go. We have this thing called the Ultra Ethernet Alliance now. And TensorTorrent is essentially taking it one stage further and saying all the connections inside a chip, as well as between chips, is going to be Ethernet. So that's interesting. We're still waiting for them to put out some serious hardware. Startup, it's about 8 years old. They've got some demo cards out there that you can actually go out and buy if you're inclined to go tinker around with them. But it's very much a development kit, not a mass retail push or anything. That comes in a few years.
So one of the questions I do have on this topic that I haven't been able to figure out, and you may be able to help me with, is how much does InfiniBand and the networking solutions, the NVLink, probably computers more likely, do those rely on the HBMs? Or because that's one of the things that I keep hearing is that HBMs are the bottleneck, that HBMs and interposers specifically are supply constrained and that no one can get them. And if Tesla, I've heard that basically Jensen has bought up all of the supply of interposers and HBMs, and anyone who's designed, I guess that's probably, I think, something that Jonathan Ross, who's the CEO of Grok, has said in interviews, is that they specifically built an architecture that didn't rely on HBMs at all because they didn't see a path forward to be able to purchase them in the first place. Um, so is that something, like, is that true? I guess would be question one. And then question two would be, could that be a bottleneck for why Dojo is not continuing to scale, is because they actually ran into an upstream supply uh, availability issue. And if how does that affect who can build what moving forward? Like, is that going to affect TensorTorrent and Jim Keller's ability to bring their solutions to market?
So HBM, when it comes to InfiniBand and networking, is two different issues. It's as in HBM isn't used in InfiniBand or Ethernet. HBM is just high bandwidth memory, is just a way to get data into the compute chip. It's not necessarily a way to send data away. You could use it as
And
a
so that would
cache,
be
but
like on a GPU then?
yes,
Okay.
yeah, and this is where we get into your point about some of the. So the bottleneck you're talking about in this instance is actually a manufacturing bottleneck. Who can create chips where? And HBM, what machine learning has done, and especially what training has done, and the size of these models that we're doing, these trillions of parameters now, means that you need terabytes of memory on a chip, terabytes of high performance memory to be able to feed the beast at high speed. And production is only so good, and as a result, in terms of supply demand is rapidly increased, and the person with the biggest pockets is going to go and buy it and then charge their equipment appropriately, and that's what Nvidia's tending towards what $20 billion a quarter, perhaps. They're the ones with the biggest pockets that are going to go do that want to do it. You were talking about the packaging. So one of the things with high bandwidth memory (HBM) is that you can't integrate it in with a GPU or an ASIC in the same way you can with standard DDR memory. It has to be packaged close together with a high speed link. And most of this is done today at TSMC, Taiwan Semiconductor Manufacturing Company, mostly based in Taiwan. They have the leading edge process. They also do leading edge packaging. And the technique they're using is called chip on wafer on substrate. You'll hear this referred to as CoWoS. When they introduced this technology, they thought it would be used, for some GPUs, but mostly in the high performance computing, standard supercomputers that often have memory bound workloads. Turns out with AI, it's needed there as well. And so numbers vary based on who you talk to, but I believe the idea was that 2 years ago they had capacity to do 300,000 chips. Last year they doubled that to 600,000. They're expecting to double it again this year to 1.2 million. I may have a year off on those numbers. Anybody who's really that interested should go double check. But the point is, while TSMC is a company that processes 12 million wafers a year, of which about 2 million are on the high end, if anybody's interested. This advanced packaging has become the manufacturing bottleneck. So obviously they sell it to the highest bidder. And the highest bidder is the one that's already making money selling pickaxes. It's not the miners who make the money, it's the pickaxe sellers. So Nvidia are able to go to TSMC, they're able to go to the high bandwidth memory manufacturers and say, we've got demand for 2 million chips this year, 2 million GPUs. How many of those can we satisfy if we buy out your entire stock? Now, you say that Nvidia has bought everything. Not strictly speaking true. These companies do have to still save face with other people in the market such that if the demand dies off, they're still friendly. I'm under the impression that on this chip on wafer on substrate packaging, it's actually split between Nvidia and AMD. Intel has some, and a couple of the other smaller AI companies have some. And they are playing a price war. Nvidia is the only one that has justified it at volume to spend that much and get the result out. We'll see through the rest of the year the other players, not only the big companies but some of these startups, whether they can compete in the same space. The demand for this hardware right now is rife. That last I heard, if you wanted to buy an Nvidia system today, the lead time is 57 weeks. If you went to AMD, the answer may be 30. If you went to Intel, maybe it's 20. Are you prepared to wait an extra 30 weeks for your hardware? Or do you say, let's take those 8 months and make our software run on this thing that we can buy today or get in very soon? And then that can be our business model going forward. That's what a lot of the... we're going back to chip shortage again, right? But in this instance, it's AI chips, not consumer hardware, which it was before. So the worry for investors is if this is a bubble. If this is a big merry-go-round, who's going to still be holding themselves when all the music stops? And right now that's pointing at Nvidia. However, you look at Nvidia's financial results and you'd be like, yeah, they can handle it. Let's go back to gaming. I don't think they're going to make $20 billion a quarter from gaming, though. But yeah, no, very, very, very competitive right now.
So, and I guess just to circle back to Tens torrent, is the availability of HBM, how much do they rely on that, and how much will that impact their ability? I know that they do a lot of different things, and so, yeah, we don't have to go into like, RISC-V is an amazing conversation that we probably shouldn't, go down that rabbit hole today, because I know that they're doing a lot there, and they have a lot of ability to make money, but as far as, Jim's ambition to build the biggest, most high performance, most scalable training and potentially inference hardware, how does how is that impacted by this supply shortage?
So right now, there's no impact at all. The hardware that you can go and buy today, and the next generation, I always get them the wrong way around. I think it's Wormhole. Yeah, Wormhole. That all uses, that doesn't use HBM. That's all LPDDR memory, which is what we find on most consumer graphics cards that play games today. It's still high speed. It's not as high speed as HBM and doesn't require advanced packaging. Um, the generations after that, based on roadmaps that they've shown, um, makes it look like they're going down a very chiplet based route. This idea that rather than make one big piece of silicon that does everything and then attach HBMs to it, you have multiple pieces of silicon, each optimized for, maybe it's made in a different foundry, in a different manufacturing node, power and compute optimized for whichever customer needs it. It looks like they're going down that route. So if a customer does want HBM, they can turn around, use a chiplet that interfaces with HBM, and then that becomes a product. There are questions about Tenstorrent about what's going to be mass market versus customized for specific customers. It looked based on the announcements they've made about IP licensing and helping other people with their chiplet strategy, makes it look it's more likely that the latter. They're going to go from customer to customer. What do you need? What do you want? This is our infrastructure, and then what they do produce, generally available to. Well, the card that they offer now is basically a home lab card, right? It's something that goes into your PC under your desk. It only has 8 GB of memory, but it still does machine learning, and you can learn to use the software. It's great for students or for developers trying to learn the ropes of their particular hardware, such that if they do go and work for, say, an LG or Hyundai, who have both said that they're evaluating Tenstorrent hardware, they can go build software for them. So in that instance, HBM isn't a vital part of the roadmap. And I think circling back to you're saying Grok didn't design into HBM because they knew it wouldn't be available. We're actually seeing this a lot in a lot of the AI, even the hyperscalers, the Googles, the Amazons. You look at some of their AI chips, they don't use HBM because of some of these reasons. Intel's latest generation of AI accelerator, they call Gaudi 3, uses HBM, but it's not even the latest generation HBM. It's HBM2, not HBM3. Why? Because the way the architecture was built, HBM2 was fast enough. It's cheaper. There's slightly more supply. They're still limited on packaging, but that's another, that's up to them to sort out. But also to this HBM statement, training versus inference. HBM is mostly focused on the training side. Inference doesn't really need it. Training needs it. And there are fewer training hardware manufacturers than there are inference. And to your point about, would this be a limiting factor for Dojo? If we look at the 120 wafer, this 4x30 Dojo system, if I remember correctly, of the 120 wafers, 80 of them are connected to 5 PCIe cards each, and each PCIe card has 4 HBM stacks on it. So that's 1600 HBM stacks per Dojo supercomputer, which is nothing. You'll find them in the back of Jensen's sofa. So it's if one of the new NVIDIA GPUs Blackwell uses 8 HBMs, 200 Blackwells equals the amount of HBM Dojo needs, Tesla needs for a Dojo, which is nothing.
And
So
and when you say a dojo, you mean like the full exapod, right? Like the
yes,
full 3 by
yeah, 40, yeah,
40. Yeah.
yeah. There may be some other HBMs elsewhere in the design, but they would be of a minimal quantity compared to the interface cards. Yeah, so given how much Tesla would likely spend for the advanced packaging, building the chips themselves, they manufacture them at TSMC, and then all the networking and all the R&D and research and engineering that goes into that, I bet you they could overpay NVIDIA 100x on the HBMs, and it would be a rounding error in the budget for the design.
Great, that's a really helpful way to think about that for me, yeah.
Yeah, if you're building a small amount of chips, then you're probably prepared to overpay for commodity hardware like this. HBM and DRAM and LPDDR is considered commodity in the space.
So I think maybe a good place to end this conversation would be to address one of the elephants in the room of the conversation so far. We've talked a lot about how Nvidia seems like, this big Goliath that is very hard to compete with in very many ways, but the technology industry is just overrun with examples of incumbents that looked big and imposing and unassailable, and then some things change and some startups do something new, and all of a sudden that player is dead. And so I'm curious, based on the all of the startups that you're tracking and the way that you see the AI market kind of developing, where do you see NVIDIA in that context? Is their current moat something that is defensible and durable over time? Or do you think that they're actually in a position where some other players, maybe like a Tens Torrent, or, maybe it's a Grok or Cerberus, or, any of the other leading players that you're tracking that have developed a good, they've pulled in a lot of funding and have developed an actual sustainable business, do they have a shot? And what does that look like in the, say, near-ish term, the next
Mm.
less than 5 years?
I mean, yeah, it's Nvidia right now has a lead. So if they were to bottle it for a generation, it would be none the wiser. There's still such crazy high demand. If, to be honest, they just announced Blackwell, and you could easily argue they could have delayed that another 12 months and it would have made a dent, right? They could still continue to make H100s, and they'd still be flying off the shelves at ridiculous prices. The fact that Nvidia's put all this effort into the software side of things for, like I say, for 15 years, there's only one other architecture that is in any way similar to that, and that's x86, the architecture that Intel and AMD base their CPUs on. That's the only architecture that has more developers that are trained, as in go through a university degree to go learn how to program. You could say ARM as well, but ARM hasn't had it to the same degree, I guess, as the other two. And that breeds comfort. The fact that the code I wrote 10 plus years ago as a student still runs on the latest and greatest NVIDIA GPU today. Forwards, this concept of forwards compatibility. The only thing that could have knocked that software moat is this concept of frameworks, the TensorFlows, the PyTorch, the cafes, the paddles. The fact that you're writing it in such an abstracted language away from the hardware should mean that you can replace the conversion tool, the compiler that converts your code into machine code, machine language. That compiler you could have swapped out the NVIDIA one for the I don't know, the Grok one or the Cerebrus one, and that was always the goal of those frameworks. The fact that you could take TensorFlow that's generally written and apply it to multiple pieces of hardware. The reality is it doesn't work that way. If you want the best TensorFlow performance, there are directives inside TensorFlow specifically for NVIDIA. So if you start using those, you've got some amount of vendor lock-in. If you want to get away from that vendor, you have to tease them back out and re-optimize them to somebody else. But because NVIDIA has all these developers, not only internally but externally, maybe that doesn't exist for somebody else. So you have to go write your own, which takes time. And not only do you have the time cost to go build that, but also the revenue loss cost of not shipping your product in a reasonable amount of time. The thing that could upset NVIDIA in this regard, aside from the general CEO goes off his rocker, or they decide to put $1 million license on everything, is if something radical happens in the way that AI is run. So we're talking about transformers being this pivot point in the industry, and what is the next pivot? Can we predict it? Can we build the hardware to predict the pivot, or can we build hardware that would be okay for any pivot? And as we optimize these chips further and further, they become less likely able to adapt to a pivot. So you're going to have to build something new. The fact that NVIDIA stays this generalized platform for everyone means that arguably they're more suited to a pivot than most. Right? Again, their chip cycles, I bet if they really ramped it up, they can go and put a new chip in design, production, market in a year. They would leverage some of the IP they already have and all the expertise they have. And it's like video game crunch time. Those developers that work for 20-hour days with no sleep and all the caffeine they can drink. I did actually visit the NVIDIA headquarters earlier this year, and I was told only two things are free: the air and the caffeine. So they already work them quite hard, but it's a case of if somebody else was going to play big in this space, there either has to be a massive disruption, or NVIDIA has to go by the wayside. I actually did some advisory work for another YouTube channel recently about the concept of what if TSMC disappeared. Either Bruce Almighty snap disappear or war and invasion. That would disrupt the market massively. It wouldn't matter that NVIDIA is a market leader in performance. Everybody would be scrambling to build manufacturing facilities to build chips. Doesn't matter where they're built. Everybody would be designing their chips to be the smallest possible to get the most amount of chips per wafer. The targets of optimization would be hilariously different. So on the outset, no. We are getting more competitive players to compete NVIDIA head-to-head. So AMD just announced their MI300 series December 23, and they're actually shipping in volume this year. They said they're going to be shipping about $4.5 billion worth by the end of this year, mostly to clients that have already expressed interest. And so in terms of revenue share versus NVIDIA, people are thinking, well, that, NVIDIA's doing, 60 billion a year and AMD's doing 5. It's, and Intel's doing even less than that, right? So when we realize models are too big, the GPT-6s, the GPT-7s, and we have to, how do we solve these? That's when the market's going to say, well, how do we make money out of what we've already got? And this is what I was saying about inference being the workload that actually makes the money. That pivot may take the focus off NVIDIA, or NVIDIA will actually take its juggernaut of a design machine and saying, okay, let's go pepper inference now at a massive scale. They already kind of do with some products, but perhaps not with the same focus as they have done with Blackwell and then vSwitch. I mean, what the startups I track are hopeful for is to take a portion of the market that Nvidia hasn't focused on. That's where, say, Cerebras has got this massive order with their partner, working on Arabic language and medical data. A lot of countries are looking at their sovereign AI strategy. How is that hardware that's homegrown, or is that we're leveraging a startup or a known player to just so we can keep it within our own borders? That sort of sovereign nature of design. I know the cloud providers are looking into providing sovereign clouds for different regions, especially Southeast Asia, but also in Europe and Africa and South America. Um, there some of these markets are opening up. Um, tier two, tier three cloud. Let's say Grok's trying to almost be a cloud provider. Cerebras is going to be a cloud provider. Tens Torrent is they're a different tack. They're trying to be they're trying to solve your AI design needs. So if you have something that you want to focus on, they're willing to do that. Um, and it's I'm tracking like 10 different AI players in South Korea, and some of them are funded by the likes of Samsung or SK Hynix, and they're doing region-specific silicon for different markets there. One's focused on video inferencing, another one's doing financial chips, and there are people looking at optical compute or optical networking, analog networking. Just because there's so much VC money in this industry, people are trying lots of different things. Will any of them rise to the point of overtaking Nvidia? I would look at the established players first, and the revenue numbers I said between Nvidia, AMD, and Intel. That'll be the first place I look at tracking that sort of stuff.
I guess the last question that I have on that note is, we've talked about CUDA and how incredible that is, and how much developer focus has been placed on that, and it's a proprietary NVIDIA only solution. And the reason that I think Grok and TensTorrent are both fascinating to me is because they both try to basically say the best CUDA is no CUDA in their own interesting way. And so one question is, are there any other players who are also offering a different solution to, moving between the PyTorch interface and the metal that looks promising and exciting to you, or are Grok and TensTorrent, the most exciting ones on that front?
Um, so I'm not sure how much Grok is actually opening up at the metal. I know TensTorrent actually. So TensTorrent has Buddha and Metallium. So Buddha's their high level, Metallium is their low level, and then obviously PyTorch and TensorFlow is above that. The problem with, I guess I should say, AMD, they have their own software stack that's called ROCm. Intel has one API and OpenVINO. And they've got some clout behind it, and they're trying to enable some similarities. They've even got CUDA conversion tools, right? How do I convert CUDA to my language of choice? And it's important for a company like Intel that actually has like 6 different architectures that do AI, so they have to have some interoperability there. For other people in the market, especially the startups, one of the problems I have with startups is they when they start, they're all engineers. Whether it's hardware or software, they're all really focused on let's build the best thing we can do. Every startup is different, but the key thing is, when do they hire a PR person? When do they hire a marketing team? Not a sales team, a team that can go out to the world and say, hey, we as a company are doing this. For a lot of startups, that's not something they think about for a very, very, very long time. I'm talking like 5 or 6 years. And ultimately, it's to their detriment. The reason why I know so much about Tense Torrent and Cerebrus, and Grok has been making noise recently, is that they have hired marketing teams that know what they're doing, people that have been marketing silicon for 10, 20 plus years, whether it's an individual because these teams are small, or whether it's working with an agency that has experience. A lot of companies have PR agencies, even the big companies, they have internal PR and external PR, and I end up working with those. For some of these startups, they might just have one person that works part time, whose only job is to put out a press release to Newswire and then to field incoming questions and then decide whether they need to go to someone. Um, but very few actually have a marketing strategy because they don't want to spend their VC funding money on marketing, right? They don't want to they don't want to interact with the press. They don't want to interact with influencers. They don't want to interact with. They'd much rather spend 50 grand going to a conference where they're going to speak to developers or potential customers, not on a branding exercise that is actually going to make them recognizable in the wider ecosystem. My job as this sort of analyst, technical marketing consultant is helping some of those brands um, actually get recognition, get mind share, get repeatably in the talking space. I mean, there's a reason why we've only mentioned 3 of the startups today. I could talk about Samba Nova, I could talk about Light Matter, I could talk about Biren. There's also Sci-Fi to a certain extent. There's BrainChip. There's a new one called Talas. There's Tachyon, Seramorphic, OnCharge AI, Rebellions, Furiosa, Habana. Well, that's now Intel. Untether AI, Preferred Network, Cypearl, Esperanto, Sapien. Dozens and dozens of companies. So when you say what are they doing different on the software side, 90% of them are staying at the PyTorch level because that's where they are in the design cycle. That's all they've thought of. And nobody's come to them and saying, what do you have at a low level? Or if they do have a lower level, they want to keep it internal. I've spoken to these startups and they say, we don't want to release a low level language because we think that limits the amount of people that can work on our stuff. Everybody works in higher level languages like PyTorch, TensorFlow, so we're going to go after them exclusively. My snapback to that is if you get a big customer, they won't care whether you support PyTorch or TensorFlow. They will want low level access. To which the response is, well, if we get a customer that size, then we'll open it up to them because there's NDAs and disclosures. Whereas, TensTorrent's doing everything open source, and people who are going down the RISC-V route are looking at open source as well. Yeah, it's also a software team is tough. You said 5,000 plus NVIDIA engineers. I'm pretty sure it's at least double that. You speak to these companies, they'll say 60% of their staff are software, even though they're hardware companies, because it turns out customers don't buy a chip, they buy a platform or an ecosystem, a way of thinking, essentially. So you have to provide both sides of hardware and software. And for 40 years in the semiconductor industry, you were either hardware or you were software. It's only in the last few years that people have actually come out, as I say, in the last few years. Somebody will correct me and say, actually, no, 20 years ago at this conference, I was talking about co-designing hardware and software. But it turns out that it is actually really, really important. Though in most cases, designing the hardware first is usually the preferred method.
Well, thank you for your expertise today. I have really enjoyed this conversation. For any of our audience who wants to find out more about you, obviously at Ian Cutress there at the bottom of the screen, that is his X handle. You can find him there. He has a wonderful YouTube channel called TechTechPotato. You have a website called More Than More, and I'll include links in the description for all of these things for people to reach out to you. Is there any other methods that you might want to direct people to specifically on top of those?
Those are the usual ones. They have emails and everything else on it. So
Awesome. Well, like I said, I really, really appreciate this conversation. I learned a ton. I have a lot of other questions that we could talk about as well, and maybe we'll have to circle back for round 2 when you're available again to do this as well. But had a blast today, and wish you the best. And I know you've got a big trip coming up, so um, good luck in what you have coming next.
It's all about AI. That's all my trips are AI. Thanks for having me on, Hans.